capture. I'm very excited to share a little bit more about the center very briefly, and then I will turn it back over to Christophe, who will take it away. So the Center for Carbon Removal, for those of you that don't know us, is a new nonprofit. Our goal is to develop a broad portfolio of carbon removal solutions, and we see direct air capture as a key piece in that broader portfolio. We do a number of things to help support the various solutions that fall under this carbon removal umbrella, one of which is to just provide informational resources like this webinar, which we will be posting on our website. We hope that this is a lively discussion, both amongst the presenters, and then we'll open it up to the audience for Q&A. Our goal is to get all of your questions and feedback. We also have other resources available on our website. We have a fact sheet on air capture, for example, and we also have a number of external links and resources, and try to provide up-to-date news and analysis on direct air capture among the other carbon removal approaches. We're based out in California, so come say hi if you're in Berkeley or Oakland. And with that, I'll turn it over to Christophe and let Christophe explain what we're going to do today and the process. So thanks to everyone again for joining.
Awesome, and thank you, Noah. Thank you for everyone joining here. So the point of today is to demystify direct air capture technology and speak and hear from some of the engineers working in various startups around the world on various solutions that fit into pulling CO2 out of the atmosphere in the global effort to balance the CO2 budget. To give 30 seconds of framing, and then I'm going to pass it over to Dr. Sean McCoy of Lawrence Livermore National Laboratory. The reason we're talking about negative emissions is because in the latest Paris talk last December, it was decided that 1.5 degrees Celsius was a desirable limit to reach, which means holding CO2 concentrations to a certain limit. The unfortunate reality is there's no way to do that without massive negative emissions, which require a way to capture carbon dioxide and a way to permanently store it. So with that, I'm going to pass it over to Sean, who is going to go in a little bit more as far as what are we talking about today and where are we in terms of addressing this challenge.
Great. Thank you very much, Christophe. I'm really happy to have the opportunity to present today, and I appreciate that that you guys invited me to do so. So, as you said, you guys asked me to put a little bit of framing around direct air capture as a climate mitigation technology. So I'm going to do that. I'll address three particular questions in my remarks. First, what is direct air capture? What is it that this seminar is actually about? Then I'm going to talk a little bit about, as I see it, some of the near-term prospects for direct air capture technology, both for emissions reduction and to deliver negative emissions. And there's a difference there, of course, for those of you who know it. I'll review it. And then the final point is, how does direct air capture compare to some of the other mitigation options that are out there that are similar, such as CCS, carbon capture and storage, or utilization, and biomass energy with carbon capture and storage. And just by way of a quick introduction and background so you understand where I'm coming from, I started working on carbon capture and storage technologies, or CCS, and emissions mitigation, other emissions mitigation technologies back in 2003 during my PhD. I worked last at the International Energy Agency in the CCS unit, And now I'm here at Lawrence Livermore Lab. My work has focused on issues in technoeconomics for CO2 transport and storage, policy regulation, life cycle assessment. And here I'm going to be focusing on technologies and policies to deliver negative emissions. So getting back to the key question of what is it? Direct air capture, or DAC, as you'll hear it referred to, is the removal of carbon dioxide from the air and the subsequent sequestration of this carbon dioxide through geological means or otherwise, for example, mineralization, in order to reduce atmospheric carbon dioxide concentrations. So it's one technology that you'll hear referred to in the broader set of carbon dioxide removal options, or CDR options, and sometimes is also referred to as a net emissions reduction technology, or NET. Of course, the extent to which it actually delivers emissions reductions depends on the details of its implementation, and in particular the way in which that CO2 that is captured is used if it's not sequestered. And we'll get back to that in a minute. But a key point going back to the history of the technology is that the continued delay in taking serious actions to mitigate CO2 emissions, at least in most countries, has boosted the profile of direct air capture, and the aggressive aspirational 1.5 degree goal agreed to by the parties to the UNFCCC in Paris has also really brought it up in standing. So to illustrate this point, and I think to emphasize something Noah and Christophe mentioned, in a very recent paper published in Geophysical Research Letters, 3 researchers, Benjamin Sanderson, Brian O'Neill, and Claudia Tibaldi, estimate that not only do we need to reduce GHG emissions in 2030 by 30% relative to 2015 levels to hit this 1.5 degree target, but we need to reach net zero emissions in 2060 and remove nearly 15 billion tons of CO2 per year, or 15 gigatons per CO2 per year, over the long term, if we start today. And I think this really highlights the huge tasks faced by direct air capture and other CDR technologies. And so this really brings us to the second point that I was asked to cover this morning. That is, given the long-term need, which I just alluded to, what are the near-term prospects for the technology? So from a technical perspective, separation of CO2 from the air is not only doable, but as we're going to be hearing, is being done at the pilot scale today. Promising approaches have definitely been talked about in the literature. We'll be hearing about some of those, things like adsorption onto solids and humidity swing cycles, or absorption into strongly or mildly alkaline solvents, sometimes with a catalyst, sometimes without, but in a cyclical fashion, of course. And the challenge, of course, is that designing direct air capture systems is difficult because we're talking about a very low concentration of carbon dioxide in the air, something like 0.04%. And so from an energetic perspective, this is more difficult and costly than capture from some more concentrated sources that you might see in traditional, I use the term traditional, but in CCS applications. Of course, once that CO2 has been separated, it needs to be sequestered for negative emissions or used somehow to reduce emissions. And so in terms of that storage, we've seen today real-world applications of geologic sequestration, along with capture and transport, of course, in a CCS system. And they've been those examples have been slow in coming relative to people's expectations. But today, there are numerous end-to-end CCS projects that are safely and effectively sequestering CO2. Those are, for example, Statoil, Sleipner, and Snowbit projects, and the Shell Quest project in Alberta, SaskPower's Boundary Dam project, again in neighboring Saskatchewan, and there are projects in development in the U.S. today as well. And so alongside these large projects, we've learned a whole lot from pilot and R&D projects, as actually has been summarized in a recent 2015 special issue of the International Journal of Greenhouse Gas Control. So I think the bottom line here is that that geologic sequestration is doable and being done. So when you look at this, all the parts of DAC are technically feasible today. Now, like CCS, perhaps, direct air capture is economically a challenge. As I think hopefully we'll hear, current cost estimates span a very wide range, but typically are in the order of hundreds of dollars a ton of CO2 removed. And so the the ability for DAC to generate value today is difficult, particularly when we have an environment where the push to reduce emissions is relatively weak, and climate policy hasn't quite caught up to technology in this space, right? Climate policy focuses on emissions reductions from point sources, not removals from the atmosphere writ large, at least when it comes to accounting. So this is one of the spaces, this idea of creating value for direct air capture is where utilization options come into play. These utilization options could involve using captured CO2 to make polymers, carbon neutral hydrocarbons, as I think the term was coined by David Keith and some collaborators, or supply remote CO2 EOR and hence oil recovery operations. Of course, the key is to generate an emissions reduction benefit. These uses need to result in displacement of a higher carbon intensity product in the marketplace. And when they do this, these displaced emissions can provide a real substantial climate benefit, and when priced, economically support further development of direct air capture technologies. So just by way of example, the low carbon fuel standard is one which conceivably in California, could deliver could provide value for direct air capture for fuels. And currently that's priced around $80 a ton in that market. So this brings me to the final question to which I've been asked to address, and that's how does direct air capture compare to other negative emissions and CCUS approaches, such as BECCS, bioenergy with CCS, or just straight up CCS. So I've already made some remarks about how these things compare, but I think in summary, really, at the end of the day, CCS and CDR technologies, whether direct air capture or otherwise, are all driven by this need to reduce emissions. So their fate does ultimately hang on climate policy. And they share many technology elements, that is CCS, bioenergy with CCS, and direct air capture. That being said, I think there's some really important differences between at least CCS and direct air capture. I think for the first major difference is that for the most part, CCS deals with fossil carbon, and that comes with a lot of baggage. Often there's a reaction to use of fossil fuels, and the pushback on CCS is strongly related to that. Direct air capture, however, is free of these constraints to a large degree, at least potentially. The second is that the scale of CCS applications is determined by the industries to which it can be applied, whereas direct air capture can be made at any scale that's convenient. And this also makes it easier to imagine from benefiting from assembly line economics in manufacturing. And third, direct air capture can be placed anywhere on Earth, right, in proximity to storage and the energy resources, whether they be fossil or renewable, needed to power direct air capture. And in contrast, CCS is applied to industry wherever it's located, which means that you have to have transportation infrastructure to move CO2 around. So again, three, and not the only three, but three important points, I think, to my mind, that make these things different. And so I think direct air capture is a lot closer to bioenergy with CCS and its ability to generate negative emissions, but it doesn't come with the same land use challenges. So I think I have basically covered the three big questions. Again, that is, what is DAC, direct air capture? The second, what are the near-term prospects? And thirdly, how does it compare to other approaches? I think that's all I'd like to say, and I look forward to hearing more about some of the innovative technologies that are being developed for direct air capture, and hope I can answer questions and participate in the discussion following the other presentations. Thank you.
I think that was an excellent framing. So now we're going to get into some of the companies that are actually doing the work and can speak a little bit more about how their technology works and various options in the short term. I do have to apologize that Christophe Gibald in Climeworks is having technical difficulties and will be unable to attend. I can present briefly for Climeworks when we get to them, but we are going to start with Anna Stukas from Carbon Engineering.
Okay. Thank you, and good morning, everyone. I am sort of pinching in at the last minute for Jeff Holmes, who's Carbon Engineering's Director of Business Development. He is the one who put the slides together. I'm our Director of Government Programs, so I apologize if I'm not quite as polished as Jeff would normally be, for those of you who have heard him speak before. So Carbon Engineering's Direct Air Capture technology is based on a strong aqueous alkali solution that is continuously cycled through an air contactor. As it's cycling through that air contactor, the strong alkali solution reacts with the carbon dioxide in the atmosphere to form carbonates. That CO2-rich solution containing all of the carbonates is then transferred to what we call a pellet reactor, where that capture solution is recycled and the carbonates are deposited onto pellets. Those pellets are then transferred to what we call a calciner, where they are heated up to very high temperatures, and that heat causes the carbonate pellets to separate and liberate their pure carbon dioxide and return calcium oxide back to be recycled through the process. So it's a two-loop process. At the moment, we model this process based on getting all of both our heat and our electricity from natural gas, which is where the numbers at the bottom of the slide come from, that for every ton of carbon dioxide that's captured from air, we use approximately half a ton of CO2 from natural gas, which provides 1.5 tons of delivered CO2. In the future, we look to transition away from using natural gas for our electricity purposes and look to potential renewable sources to provide the heat, which we anticipate will reduce that significantly. But for now, we're presenting the conservative system schematic. And this gives us nth plant costs on the order of conservatively $100 to $120 per ton of CO2 captured. What carbon engineering is then doing with that CO2 is the subject of the next slide. So we see a role for direct air capture in both accelerating and enabling the penetration of renewables into the transportation market. As has been noted in this graph and by the IPCC and the National Academy of Sciences, we are going to require broad adoption of renewables as well as carbon removal in order to meet the temperature targets that have been set. And we see that as a two-pronged solution. First, if we use that carbon dioxide that we've captured from the atmosphere to create synthetic fuels, it accelerates the adoption of renewables. And second, we can then use that carbon dioxide and sequester it to address the carbon removal portion. So the schematic that's up on screen right now is a pictograph of the potential market opportunities for that CO2 that you're capturing from the atmosphere using DAC. You can either put it straight underground, and that in putting it straight underground, it can either be permanently sequestered or used for enhanced soil recovery, which is not something that we are focusing on. Or, as CE is currently focusing on for its near-term market opportunities, you can take that carbon dioxide, you can combine it with hydrogen that's produced from renewable sources, go through a fuel synthesis process and create synthetic hydrocarbons that can then be used in the transportation industry as a complement to other means of decarbonizing transportation, such as electrification, hydrogen, and biofuels. And we see this as having particular applicability in heavy industry, long-haul trucking, heavy machinery, and aircraft, where it isn't as easy to address decarbonization through electrification, and see further advantages that this is eminently scalable in a progressive fashion. You can start at 1% and theoretically scale all the way up to 100%. There isn't a blend wall such as you would see with ethanol where you can't go over about 10% before you impact your engine performance. So that, Christophe, I think I've kept that to my allocated 5 minutes. Gives you a brief overview of carbon engineering's technology as well as where we're focusing on for near-term market opportunities.
Awesome. Thank you, Anna. And I look forward to going deeper into it. So unfortunately, Climeworks cannot participate, so I will pull on what I know about their process in order to briefly present it. They are a startup company out of Switzerland. They came from EMPA, which is the Materials and Science Technology Lab there. They use a mixture of heat and pressure here. You can see the schematic that they use heat at 100 degrees Celsius. They have a contactor that, much like carbon engineering, uses a fan to pull the ambient air through a material. They will then use heat and pressure to get it off. They have 3 different sized modules. CO2 collector, you can see the smallest module, and then the direct air capture plant, you can see the largest one. And currently, they are feeding a greenhouse in Gadza, Switzerland, around 3 tons a day, and they are running a demonstration plant. They also are able to provide CO2 for beyond just greenhouses. They have pure stream of carbon dioxide that can be used for carbonating beverages. Here you can see couplers. And similarly, they're looking for on-site CO2 creating liquid hydrocarbons. I note that their large and long-term objective is to get good at pulling CO2 out of the atmosphere in order to sequester massive amounts of. Sorry, this is a bit of a brief, but I don't want to say more about a company when I don't work inside of it. So we are going to transition to Skytree. All right.
Great.
Take it away.
Thanks, Christophe. Thanks for the invitation also to Noah to be at this webinar today. I think this is a conversation that needs to be had more frequently between knowledgeable people in the sector because it's important, as we've just acknowledged. So to get straight into it, if we could go to the next slide, please. Christophe, can we go to the next slide? That would be great. So basically, there we go. Oh yeah, got it now. Yeah, cool. Sorry about that. So our technology works using solid amine material, and the process works by exposing the material to ambient air and using a fan as well, and allowing the CO2 to diffuse into the material and be absorbed onto its surface through adsorption. The material is a type of ion exchange resin that's been tailored to low concentration CO2 gas streams. And it was actually not selected or developed by us, it was actually developed by the European Space Agency after rigorous selection process analyzing a few different types of solvent. So we are simply, let's say, transferring this technology. The benefit of the material is that, unlike liquid amines, it's very benign. Liquid amines also suffer from evaporation when you're passing flue gas through them. This material is very stable. It can last up to 5 years with minimal degradation in performance, depending on the environment. And it also only requires low-grade heat for regeneration and has a lower heat capacity than you can find in liquid amines as well, because it has a plastic support. One of the things that that makes it so good and effective at capturing CO2 is that it actually has very high surface area. So it's extremely porous, exactly about 50 square meters per gram to be precise. So this allows it to uptake a good few percentage points of its own weight in CO2 over the absorption cycle. The prototype, so that's the material and the process. What we actually have working right now is a little bit smaller than Climeworks, at least. It's a 60 gram a day prototype, which can produce over 99% CO2 purity concentration and an average of over 95% over the whole cycle. It's fully automatic, and we have sensors embedded, so we can characterize the process and improve it. So we measure flow rates, CO2 concentration, temperature, pressure, and all the other parameters that are useful to know surrounding the absorption process. A cycle at the moment takes about 12 hours, so we run about 2 cycles a day, finally, we also have, we're also testing ways to compress this CO2 output and store it as well, so that we can become closer to final application. Okay, next slide, please. Great. So that was the technology. Now the markets for us are very important because we see 2 sides to our technology at the moment. We see CO2 supply, where basically what we would be developing is clean CO2 generators, which could be coupled with, for example, urban greenhouses or water purification plants, and essentially would provide convenient on-site access to CO2. The disadvantage of existing systems is that cylinders can be bulky, hard to use, and has to be replaced every few weeks, and they're also under high pressure. So on the supply side, we offer convenience and better safety. We're also looking at extraction. Now on the extraction side, it's a little bit different, but it's relevant to that technology because it uses quite a similar process and similar materials can be used. Here we actually sell air quality. So we can improve air quality by scrubbing CO2 from closed environments, let's say hotel rooms or planes. And what this allows is not only better air quality, but actually more air recirculation, or the potential for more air recirculation. And that means if the air can be recirculated more easily, less outdoor air has to be brought in by the ventilation system, which in turn would otherwise have to be cooled or heated. So we can also provide energy savings with our extraction business. So we have extraction and supply. To go into detail on the supply very quickly, we're talking with urban greenhouses. We've recently worked with a maritime company for water purification on ships, and we're currently in a project which is developing a household methanol generator. This is an EU-funded project based in Germany, and we've been selected as a contractor for CO2 supply from the air for that system. I think that's all I have right now. We're also talking with a partner on extraction for ventilation from a closed cabin. So we have existing customers that are paying to develop this technology and want to see it scale and want it today, which is really good. Thank you.
Awesome. Thank you very much, Max. Keith, are you there?
I am. Thank you.
All right. Take it away.
So this is Keith Gadza. I've been working on commercializing a technology that was first worked on by Dr. Lochner, who's now at Arizona State. It functions on quite a different technology or process than all other types of gas absorption technologies, which usually they bring in the energy through either temperature or pressure. This one has been coined the humidity swing because the chemical reactions are reversed with the presence of water. So the materials that we use, they absorb CO2 from the atmosphere, and when it's dry, and by the addition of a little bit of water, they will release that CO2 in concentrations up to 100 times atmospheric concentration. What we're currently doing is taking this technology and commercializing it. The benefits of this technology is that it's ideally suited for maximizing the growth rates of all photosynthetic organisms. It produces streams that are, 5 to 10 times more than they actually need, so we can feed that into enclosed environments to double the rates of plant growth. So that is the markets we're going after. We provide that so it's not a pure stream of CO2, but it is a concentrated stream of CO2. The advantages of just going to this is that we're doing less work on the compression, and all of these things are energy savings that allow our targets are going to be well below $100 a ton for the CO2 that we can provide. If you can go to the next slide, I'll see what has been provided.
Keith, I actually didn't make slides for you, so you have one slide.
I thought maybe you got them from someone else. So.
No, I just.
But I'm happy to answer any questions when we get to that phase on the technology itself or the specifics on what we're going after.
I'd love to get the presenters' views on near-term policy options. That what we've heard a lot about is there's this great potential, but there's really a long way to go in turning these initial markets into large-scale carbon removal systems. So I'd love to hear from the panelists about what policies they are looking at in the near term to help drive their commercialization and what they see as the most important policies that either exist today or are on the table to discuss in the future for really helping to scale up our current systems. So maybe Anna, would you like to start? Yeah, go ahead.
Yeah, absolutely. So from our perspective, we see two mechanisms that are available. The first being a broad-scale carbon tax, and the second being low-carbon fuel standards. Now, a broad-based carbon tax is useful. It will be necessary to eventually enable the sequestration and storage market, because until carbon dioxide in the atmosphere is treated as a waste product that needs to be mitigated and needs to be paid for accordingly, the market for storage and sequestration, it doesn't have a huge market driver. It's like sewage treatment or other waste disposal means. So we see that as a necessary long-term policy lever that will need to be exercised. And to the extent that that lever can be harmonized to the greatest extent possible, we feel that that will be necessary in order to encourage broad-scale adoption of sequestration. In the nearer term, we see incredible benefit in the application of low-carbon fuel standards, such as those that are seen in California and in British Columbia already, because the particularly useful thing about these mechanisms is that they drive a very high price on carbon. Average prices in California in the past year have hit over $125 a ton, and I believe are currently hovering around 80, which is certainly higher than any of the carbon taxes. And what the LCFS does is it allows that premium to be transferred in large part to the entity that is developing these innovative synthetic low carbon or ultra low carbon, carbon neutral fuels, while only transferring a fraction of that cost onto the end consumer, which we feel is critical to ensuring viability of these regulations in the long term. You can imagine that if people went to the pump tomorrow and suddenly found that the cost of gas had doubled, that there would be huge public resistance. By contrast, with these LCFS policies, they enable gradual decarbonization where the end consumer is only seeing that premium on the fraction of the fuel that is low carbon, that is getting you to the overall reduced carbon targets for your transportation fuel, while enabling that higher premium to go direct to the synthetic fuel producer, and therefore incenting innovation in the carbon neutral fuels market. So that would sort of summarize both our long-term and our short-term policy focuses.
Thanks, Anna. I'd love to hear from Max, too. What programs in Europe are you looking for? Because I know there are some higher-priced carbon markets in certain jurisdictions. Is that a key policy driver, or are there other things on your radar?
Right. Well, we're not really looking at carbon sort of policy at the moment that could subsidize the technology. There are definitely, carbon credits. There's still a carbon credit market here, but the price isn't too high, I believe. But it's argued that as long as you can get the price of DAC CO2 somewhere between $1,500 and $80 per ton, so it's quite a range. If you can get within that range, you're okay to commercialize in certain markets, where the higher end is a small scale, more niche markets, and the lower end, the $80, is more real commodity market producing fuel, plastics, and so on. So I would take it a step further and say that we don't really want to. It's not necessarily always healthy to depend on subsidies as a company, because what happens if those are suddenly taken away, right? This happened kind of in Germany with solar panels, where suddenly there was less subsidization in solar power markets, and a lot of the companies ran into trouble there. But what about other types of policy like cradle to cradle or upcycling policy that is applied to companies in our sector that could be potential users of CO2? So if they could benefit from using upcycled CO2 and recycled CO2, that will make it more likely that they would go for that solution.
Thanks, Max.
Thanks, Max. Keith, do you also look at certain policies for energy, or I know that your target market is greenhouses right now. Are there relevant policy steps that will help you there?
That's unfortunately not my area, but with the fact that we produce such inexpensive CO2, we have strong commercial drivers for our products and our machines. But it's going to benefit all of us to have the political will and the incentives to encourage current greenhouse owners and future ones to move into these more efficient ways of growing plants and other organisms. So the incentives are going to help everybody.
Thanks, Keith. I want to throw this back to, because you are the National Lab and you think a lot about policy drivers, and we've already heard a number of small markets that are maybe incremental on a pathway to large-scale negative emission. What do you think would help?
Well, thanks, Christophe. I mean, I think first, I think it's a really worthwhile point, that to keep in mind that I think there seems to be in all climate policy and a lot of these climate problems a disconnect between where we are today and where we want to be in the distant future. And I think that it's pretty smart for technology developers, like we've just heard from the others on this webinar, to be focusing on kind of the near-term markets that can get incremental improvements and development in their technology, right? And those often aren't related to climate policy directly, right? Obviously, you know, the discussion we just heard from carbon engineering, where, you know, the LCFS is a potential driver. Well, that is a little more tied to climate policy, but again, even there, it's not about reducing emissions; it's about reducing emissions intensity. And I think this is smart because I think, and by analog, if you look at the story of CCS, right, for the longest time, CCS was pretty much talked about only as being driven forward by big, strong climate policy, carbon taxes and things of that nature that just haven't materialized, and it's really left that technology in a tough spot. So I think the idea that you can look at some of these near-term drivers is very important. And I think the key issue is how you get from these smaller niche, if I can say, markets and non-climate drivers to the broader carbon drivers, and how the technology can be adapted to fit into delivering that, you know, billions of tons a year of CO2 emissions avoided. And I think I'm not sure how that policy transition works, and I think that's a big question, of course, for the energy system as a whole and society as a whole as we move forward. So I don't think I have any particularly great answers on that one right now, but I do tend to think that policies like carbon taxes will probably be involved, at least in certain sectors, and could very well be that air capture plays a role there.
Awesome, thanks. Okay, the next question I want to ask is related to, let's say that I wave a magic wand and all of you have all the money and human resources you need to build and deploy your technology. What does it look like in 2 years? What does it look like in 5 years? And where are we in 20 years? Anna, let's start with you.
That's a tough one. If I had my magic wand and all the money I wanted. So I guess to be a little bit more realistic than simply waving a magic wand and launching in headfirst to mass deployment, what we would see in 2 years is to be moving towards first commercial plants in jurisdictions that have a combination of factors that make air-to-fuels make sense. So for us, that would be jurisdictions that have large quantities of either low carbon or carbon neutral electricity available, and further that either have policy mechanisms such as low carbon fuel standards or industries or organizations that have committed to or are mandated to commit to drastic carbon reductions. So an example of that in British Columbia is that if you take our provincial government at face value, they would claim that 97% of our electricity is low or carbon neutral. We also have a public transit system through BC Transit, who are committed to deep cuts in carbon emissions and eventually to become carbon neutral on a fairly aggressive timeline. So we see opportunities like that and comparable ones in locations like California as the ideal location for first commercial plants. And we would, in an ideal world, be moving towards those commercial plants within the 2-year time frame. From the 5 to 10-year time frame, we would see that broadening out as the cost of solar continues to drop. We're aware of sort of 3 cents per kilowatt hour solar in places like Qatar being rolled out at large scale. We would see that as being a primary driver to enabling feasibility of broader scale deployment of these commercial plants, with first commercial plants looking on the order of 100,000 tons of CO2 to be removed every year, and the sort of 5 to 10-year goal of those commercial plants being in the megaton range. So that's a megaton of CO2 every year. From a 20-year perspective, we would want to see aggressive growth to enable broad-scale global deployment of these plants, initially going into the, I suppose you could call it a niche market, but it is $3 trillion a year of transportation fuels. And we would hope that by 20 years from now that we would have the carbon policies in place to be able to transition from simply recycling the carbon and displacing the use of fossil fuels to being able to sequester that CO2 and begin the process of true negative emissions. So that's where we would go if we had all the money in the world, but still wanted to take a fairly pragmatic approach towards it.
Thank you. Max, then Keith.
Yeah. So like what Anna said, but just maybe a bit slower. I think the 20-year time frame is definitely something that I agree with. I could see as an opportunity for DAC technology to be used for carbon mitigation. That's a long time. That's a lot of R&D. That's a lot of time for economies of scale to be found and efficiencies to be improved. Right now we see some challenges that even if we had all the money in the world, that still would take time to sort of overcome. So in 2 years, I could imagine larger pilots, having been implemented and us having undertaken more research into optimizing the efficiency of the process. And 5 years, I could see with unlimited resources that there would be commercial implementation of systems supplying, substantial kilos of CO2 in different commercial sectors. So in short, we're compared to climate engineering, carbon engineering, sorry, we're taking maybe more stepwise, iterative commercial approach to the market. So we would implement it sooner into these so-called niche markets, which would necessarily be on a smaller scale because a lot of these markets don't need that much CO2. But then we would be, through continued R&D and development of the technology, we would be at a place in 20 years, I would say, to be applicable for carbon mitigation. That's my summary.
Great, thank you. Keith.
One of the nice benefits of the technology that Infinitree is commercializing, it's been under development for a while, and we're actually in the phase of scaling and commercializing. So that the other things are that our systems are quite simple. It's like most of these, the contactor is the key technology, and we're already along the ways of scaling that. The rest of everything are relatively standard, simple components that can be mass produced in any quantity that we want. So with a magic wand and unlimited resources, we could scale to any scale needed that the market would divide. We have huge demands for this technology because we're already at an attractive price point, so that in 2 years manufacturing is scaled to the equivalent of the auto manufacturing. 5 years, most of the current world's greenhouses have been supplied, and in 20 years we have revolutionized the way how most food and organisms are grown for energy production. All these things could be changed relatively quickly with a huge amount of funding.
Great, thanks. So we are going to go from being wildly optimistic to grounded in reality, and I'm going to ask actually a question from Peju with Virgin Earth Challenge, which is to look at, so what are the roadblocks? What are the external challenges that you face today as a business? And then maybe put a flavor of optimism and think, okay, well, what could be done to alleviate these challenges? So whether this is a technical challenge, a policy challenge, we'll start again with Anna.
So I suppose from a technical perspective, and part of why I think we took an aggressive position when we had the unlimited money in the world scenario, is that we do have a full end-to-end, full-circle functioning pilot today that captures a ton a day of CO2 from the atmosphere, ballpark. That up until now has been a catch and release program, but we're currently in the process of deploying a pilot extension that will allow us to take that CO2, capture it, combine it with hydrogen that we're going to be producing on site, and on-site process that into synthetic fuels. So we're well underway with that pilot process with funding from the British Columbia government, and view that, you know, largely a lot of our sort of core scientific challenges are things that we've overcome. And I think the other aspect of that is that our pilot, instead of being designed as a, you know, how big can we go perspective, instead we engaged commercial vendors and said, how small can we go and still be representative of commercial technology? And so the selection of the pieces of equipment that we have in our pilot at the moment have been based on the size that's required to validate commercial performance of our technology. So we have been methodically crunching through those technological challenges over the course of the last 6 years, and more particularly over the course of the last year as we've been operating our pilot on site here in Squamish. So that for us really isn't a major concern. I mean, obviously there will always be continued engineering and optimization required, as there is with any technology, but we don't see that as one of the key risk areas at the moment. We do see the need for policies around low carbon fuel standards to be more broadly adopted, and to be adopted in a more harmonized manner. We're facing a scenario in Canada right now where the premiers of all of our provinces came out of their annual meeting about a month ago and said that they feel that they should be adopting whatever carbon pricing policy works for their province. And we feel that it is incredibly important, if we are going to enable widespread adoption of DAC technology or of any carbon mitigation technology, that to the extent possible that those carbon policies, be they carbon pricing or low carbon fuel standards, be harmonized across jurisdictions and that they be performance-based. We feel that it's important to allow any solution, even these transformative ones that take CO2 out of the atmosphere, to be able to compete, and regulations that preferentially prescribe certain technologies over the others, they don't help. So we see a lot of work to be done on the policy side to broaden policies such as those that already exist in California and British Columbia. And then I think from a financial perspective, we've been very lucky with our funders. We have very supportive funders, and we've had a lot of support as well from our federal and provincial governments. But we can see that there's always a need for more support from governments to recognize the need to fund transformative technologies that address the 95% problem of all of the CO2 that's in the atmosphere, rather than focusing on that first 5% and all of the low-hanging fruit, like let's put 5% ethanol in all of our gasoline. and instead having a view to incent the development of technologies like air-to-fuels. So I think that's sort of where we would focus on overcoming some of those hurdles.
Thanks. Max?
Okay, so I could chip in there. So to answer Paige's question on the main challenges and obstacles facing us and as a direct air capture company, I would say it's two main points. It's technology and it's perception. So on technology, the main challenge we have right now is scaling. So the more CO2 that needs to be captured, in the case of Skytree's process, the more sorbent is needed and is required. And there's a cost to manufacturing that sorbent. This needs to come down. This will come down with economies of scale as we can order more. And it will come down with efficiency optimization. However, we think that ultimately the way we need to go with this is to bring it in-house, learn how to synthesize it ourselves so that we can scale up internally, and we can implement optimization and efficiency measures directly. We're not there yet for large-scale capture, but we think we can get there. Another challenge that we have for large-scale capture is energy requirements. Again, if you look at coupling the process with waste heat or renewable energy like solar power, geothermal energy, then we overcome this difficulty as well. Solar energy can be very, very cost effective over a long time span, and that's what our technology will operate over anyway. So that's where we are very openly on the technology. Lots of challenges, but we can get there. On the perception, the main challenge we have right now is that DAC is seen as a alternative almost to CCS. So it's kind of putting two next to each other when actually maybe the comparison isn't completely accurate. Perhaps it's better to compare carbon capture and sequestration to alternative energy forms, such as solar energy generation, and renewable energy generation. This is actually the idea came out with recently with a conversation I had with Tai Lim, and I think it really holds true. The fact is, you can't commoditize carbon from a CCS plant because you're putting it underground. So it's not really a commodity that can be sold. Essentially, you're burning fossil fuel, CO2 is emitted, and then you have this huge technological process to put that CO2 back underground. Just from a basic perspective like that, objectively, it seems kind of difficult, and there's definitely challenges with CCS, as we know. Whereas with that technology, because of its location flexibility, its ability to be implemented on smaller scales, and its also ability to be scaled in terms of mass manufacturing, whereas a CCS plant would have to be designed in a bespoke manner for every single power station. A DAC module could be mass manufactured. We're in a much better position to supply CO2 as a commodity in a lot of markets. And in that way, then you're comparing DAC as a cradle-to-cradle CO2 supply solution compared to existing carbon-positive CO2 supply systems. And suddenly, DAC then looks a lot more interesting, at least in the near term, as a commercial route. And back to Anna's view, I totally agree that we need to get there eventually, and this is one of the reasons we started Skytree. Carbon mitigation, it would be great to have a solution to that one day. But there's huge potential for CO2 usage as a cradle-to-cradle commodity in terms of fuel production and, as Keith mentioned, organic materials. So that's my view in a nutshell.
Thanks. And there's a lot in both of your commentary that I'd like to pick up on, but Keith, I'd like to give you a chance to talk about challenges to overcome. The floor is yours.
I think it's been mentioned. You know, the challenge for any new technology is the perception of risk from your early adopters, and you know, as some mentioned, is to keep things in house to demonstrate it. So you know, I guess that would be our biggest challenge is finding the right niche markets or the right groups that are going to be early adopters. They're going to take the little bit of risks that are associated with running something new that they're relying on their businesses for. So you know, that's the challenge we're all going to face as we move from development to commercialization. And so we're facing that relatively soon. I mean, we definitely, it's not something that is a huge deterrent. It's definitely overcomable, and we're working through that. But I think that's true of any technology is perceived risk because it's something so new.
And I actually think that's a really nice segue into my next question, which is about perception. And what are some of the biggest misperceptions, misconceptions of direct air capture technology as it relates to, I don't know, maybe this is something that is just thermodynamically impossible. This is something that might delay emissions reductions. Maybe this is something that might cause more problems that didn't exist before. How are some of those misconceptions actually not necessarily true, and how can the processes your companies are working for maybe begin to deconstruct that? Anna, do you want to speak to those, or maybe anything else that you think is worth clarifying?
Yeah, I want to pick up on something that Max said about DAC often being compared to CCS. And this is something that we've had raised in recent months as a criticism against DAC to say, well, why would you bother to create synthetic fuels from atmospheric carbon, which, as we all know, is a very dilute source, when it would be, and I quote unquote, much cheaper and easier to capture that carbon from a more concentrated source such as a flue stack. And I think, first of all, we would question whether or not it actually is cheaper and easier to capture that CO2 from a flue stack. It may or may not be. We'll leave that out there. But the fundamental issue that is missing when that question gets asked is that if you capture CO2 from a flue stack, where that flue stack is, say, from a coal-fired power plant, and you then create a synthetic fuel with that CCS-derived CO2, that you still essentially have a fossil fuel. And consequently, you don't have the advantage of the significantly lower carbon intensity associated with that fuel that you would if you created that fuel from atmospheric CO2, where we like to think of it as more you're recycling that CO2. And that seems to be an issue that comes up sort of again and again. And a secondary question is, well, why are you focusing on atmospheric CO2 when biofuels give you reduced carbon intensity and are available today? And we would say, yes, absolutely. Biofuels exist. CCS exists. They are both good technologies. They are both necessary technologies. However, they cannot address the entire problem. With CCS, you need it as a mitigation, but ultimately it doesn't drive you away from fossil-based power or fuel. Biofuels are great, but they're ultimately going to have a scalability problem where at some point you're going to run into competition for arable land with our food sources. So that perception challenge is something that we definitely see, and that we can see further public education being useful, because, you know, first of all, that we see DAC as a complementary technology, but also as one that has significantly greater potential to scale and meaningfully decarbonize these sectors. So that, I know it hasn't tackled all of the challenges, and I don't think I'll go into the rest of them, because I think we could spend all day talking about different perception challenges. But those are two of the very near-term challenges that we see and that we're grappling with today.
Thank you. And I can attest, having visited your pilot plant, that it does indeed work and deliver CO2 as promised. Max, do you want to chime in?
I mean, I really wouldn't have too much to add. Basically, yes, I think Anna was spot on with the comparison there, that, you know, fuels supplied from a DAC CO2 supply source would be truly carbon, you know, neutral. What happens when we're not burning fossil fuel anymore and we don't have a carbon supply, you know, for fuel production or other production, you know, from CCS or CCU system based on a power plant, you know? So in the long term, definitely, you know, for that, DAC is the answer, and CCS and CCU on from a point source can't compete with that. The final thing I would add would be that people also forget the different types of business models that should be associated with the technologies. So I think there are definitely different types of business models that need to be considered when talking about the different types of carbon capture technology. And finally, sorry, I had a point here. Basically, there is an advantage with the fact that, to just quickly compare, the fact is CCS doesn't require so much space to capture the equivalent amount of CO2. And it is more energy efficient. That is true. But in the long term, DAC is scalable and can be made more efficient, and is really what we need as a sustainable society.
Thanks, Max. Sorry, actually, Sean, if you want to pick up on some of the conceptions or misconceptions that Anna was talking about.
Yeah, I think both Max and Anna made some really good points, and I think that particularly to Anna's point about the understanding of kind of what you'd call the life cycle impacts, or the life cycle assessments of these sorts of processes, whether they be CCS or a fuel derived from direct air capture. I just think there's not a really good handle around that. I think that even for those working in the LCA space, some of the issues, the life cycle assessment space, some of the issues that get pulled up there are really complicated and difficult to deal with, and they don't have clear answers. So I definitely completely agree that understanding over at a very large sort of systems perspective what the emissions impact of these technologies are, whether they're delivering, you know, just emissions reductions or truly negative emissions, is difficult to really get your head around. And I certainly can think of many times when I've seen presentations where, you know, people have made some outlandish claims about what they're doing that have involved CDR, and you know, and it's so that, you know, I think there's an onus on everyone to make sure that they're being real about what they're pitching with these sorts of when they talk about emissions reductions or negative emissions and direct air capture. So definitely agree that's a challenge. And same with CCS. The CCS community doesn't even get their head around some of these utilization issues and the ability to reduce emissions. That they don't have their head around that either, in my opinion. And on the point about kind of the whether I completely agree with Max's point that CCS and direct air capture are complementary, and I think Anna would have said that too. I think that and not necessarily substitutes, but people seem to be looking at them that very much that way, and I think that's in part because at least in some of the funding space, they are treated in the same kind of pool, and so it is a bit of a zero-sum game. At least I get the sense that that's the situation in Europe, particularly with commission funding. And I think also some of the, there's been a fair bit of academic controversy, you know, at conferences and things earlier, about, you know, well, your thermodynamics aren't right, or you know, you've made mistakes in these calculations, or your cost estimates aren't consistent with the way it's done for CCS, or various things like that that have also put at times a bit of an adversarial spin on the relationship between CCS and direct air capture. But as I said, I think they are substitutes. I do not think they have the same business models at all. And certainly not today. And I think, as I mentioned in my beginning remarks, there are a lot of factors which really make these things different. And as Anna said, you're not dealing with fossil carbon, at least for the most part, in direct air capture. And you are, at the end of the day, with CCS, you're trying to mitigate the emissions from fossil carbon use. So big differences there that I think make these things more complementary than substitutes.
Thanks, Sean. And that actually segues very nicely into some questions that I'd like to rephrase from questions from the audience. As we talk about life cycle, a lot of numbers need to be thrown out there. One is, okay, what are the energy costs of capturing the CO2? But the distinction, I think, with direct air capture is in some cases you might not be providing CO2 that's pure. Maybe the source that needs it is not. You might be recycling it. You might be injecting it underground and disposing of it. Each process kind of comes with a different cost. So if each startup participant could just speak a little bit about system boundaries, energy costs that it sort of takes to get you from capturing CO2 out of the atmosphere to another form, whether that's just CO2 enriched air, such as in Infinity's case, or otherwise, and how you go sort of wrapping your head around today's costs and end costs. Keith, would you like to start?
Sure. So I think when a true carbon balance should have no boundaries on it. You should consider the carbon input into making the machines, the processes for delivering, all of those things, because all that really matters is that number right now, what, 402 parts per million in the atmosphere. So drawing a box around something that makes it look good isn't really doing anything if you're expending lots of energy somewhere else. So I think that's one thing that I think that the industry needs to be true to themselves is to just consider all of the energy expended anywhere in these activities, and then you can take credit for making impacts on the actual atmospheric CO2. That's my one comment on that side of where you draw your boundaries. There shouldn't be any.
Fair enough. So would you like to maybe spend 30 seconds on the moisture swing process and how that consumes energy? Yeah,
so because we are supplying a commodity to somebody that wants it, and one of the keys is to supply it as they need it. So we do expend energy moving air through our system like a lot of the other ones. So we do expend electricity that is going to come off the grid to power air fans in a small motor within our system. With our current materials and our current off-the-shelf components, we are capturing 30 times the amount of carbon that is expended on the electricity. That is reduced by a small fraction if we take the full carbon hit for the energy expended on making the materials, the metal and whatnot. That improves as our grid power and the cleanness of our grid. We do expect to get to in the future with a highly renewable energy supply and improvements in our slight improvements in our process and efficiency to a 100-to-1 ratio of capturing CO2 from the atmosphere versus the amount that is ultimately released into the atmosphere.
Thank you. Max.
Yeah. So I would say it's about a 1 to 4 for us in the long term in terms of CO2 emission versus CO2 captured from the air. The electricity consumed to capture that CO2. I would say that's quite a conservative estimate. And of course, it depends where you get that energy from as well, right? So if you're burning natural gas, it's a lot different carbon balance to if you get it from a geothermal source, right, or a solar power source. That's where we are in the power consumption. And in terms of scaling up the efficiencies that we could reap, well, one clear, very, very practical difference is that on a small scale, currently we're using electrical heaters to heat up the material. Once we go to a larger system, say anywhere over 20 kilos a day, that would become very inefficient and not practical anymore. It would just become very expensive and difficult to implement anyway. So we would naturally then tend towards probably a water-based heating system that then could benefit in turn from concentrated solar power or geothermal energy or whatnot. Which then will bring natural efficiency to the process. On top of that, with a bigger system, the insulation will be better as well. So we'll be able to enclose the cartridges more. They will be surrounded by more of the material itself, and the efficiencies generally will tend to be better with scale. Right now, with our smaller systems, we get a lot more heat loss, than we would on the larger scale.
Thanks.
So that was my answer.
No, that's great. And you want to also give a little bit about energy costs and cost reduction opportunities.
Yeah, and I guess to start with, I would say that we absolutely agree with Keith that when you're looking at the carbon balance, there is no boundary. You need to take into account everything from the carbon associated with building that plant and the carbon associated with your feedstock materials, all the way up to the carbon associated with disposing of that plant at the end of life. So we 100% agree that you need to be really taking into account that full life cycle, cradle to grave carbon emissions on that front. From an electricity perspective, we would draw that boundary sort of at the fence, colloquially. So we consider basically that everything that goes in to produce CO2 out the other end, generically we think of that CO2 coming out in a compressed and purified form. So we would think of all of the power that is required to go straight from capturing that CO2 out of the atmosphere through regenerating the capture solution all the way to that pure CO2 out the other end as being sort of part of that power requirement. So as you can see on our slide, in the most conservative estimate, and the CO2 there is just the operational amounts. That would be a case where you're deriving all of your power and all of your heat from a natural gas power island and using natural gas to provide the heat as well. For us, the biggest source of, or the biggest draw of energy inside our plant is the heat that's required to liberate the CO2 from the carbonate pellets. And for us, that is something that drastically improves as we go to scale. In our pilot, a huge amount of the things that we have associated with our calciner are to simulate the conditions that you would see commercially, because our pilot calciner has such a small diameter and therefore a small internal volume relative to the overall surface area. So you see a lot of heat losses in the pilot that are not at all representative of what you would see in a commercial system. We see efficiencies sort of maximizing when we can leverage the biggest scale calciners that are available. You see those used in the refractory industries today. They're about 6 meters in diameter. And at that point, you get much greater heat efficiencies because you've got a much greater volume to the exposed surface area. So you're seeing a great reduction in heat loss. So we've put a very ballpark 10 gigajoules of natural gas on our process basic slide, and we see opportunities for efficiencies in that as you scale up. Great, thank you so much. And to stay on the clock, we're actually going to wrap this up. I would like to thank all of the speakers. I apologize for any technical difficulties we had earlier. I truly think this is an exciting topic. I believe that it is the very early days of a learning curve that we can go down, and that learning curve requires doing. So it is extremely exciting to be connected to those startups who are doing. I'm going to pass it over to Noah to close it up, and thanks to Center for Carbon Removal for sponsoring this webinar.
Yeah, thank you, Christophe, and thanks to everyone who presented and participated. We'll make sure to post this online, and don't hesitate to reach out to us with any other questions that you have. You can get in touch with us through our website or via Twitter. We're at Carbon Removal. And thanks again to everyone, and look forward to continuing this conversation in the future.
Thank you.
All right. Thank you, everyone.
Bye, everyone.
Bye.